Hello, everyone, and welcome to the last colloquium of this year, the last TVS colloquium of this year. Let's welcome Žiga Lesar. He's a postdoc at University of Ljubljana. I hope I pronounce that sort of okay. He's going to let us know everything about the visualization-related research. So please, Žiga, take it away.
Thank you, Priscilla, for the short introduction. We will present our visualization and graphics related research we do at the Laboratory for Computer Graphics and Multimedia. And today here we are, myself, Žiga Lesar, and my colleague, Ciril Bohak. We are from the Faculty of Computer and Information Science, which is part of University of Ljubljana. So we are just in the center of southern or southeastern Europe. It's quite a large university. We have about 40,000 students, more than 6,000 staff, teachers, administrative staff, assistants, and so on. So here at the Faculty of Computer and Information Science, it's a bit less. It's about 250 staff, teachers, assistants, and we are just a small part of this. We are working in the Laboratory for Computer Graphics and Multimedia, which currently employs 13 researchers and assistants and professors. And about half of this laboratory is actively involved in computer graphics and visualization research. So here today we'll slowly but surely go over all the different topics we are covering, all the different domains. As you'll see, it's quite a long list, quite a wide and colorful array of different research topics, and we are excited to present this to you today. So then maybe we'll see how to extend our visualization capabilities, our expertise in graphics, maybe also into the astronomical domain. So here we have a lot of different projects from many different application domains, ranging from medicine, microbiology, high energy physics, geoinformatics, material science, and education. So here under education you also have VR, XR applications, and stuff like that. So you can see already here from these few images, from these few screenshots, that it's basically a really wide array of different visualizations, ranging from visualizations of volumetric data, point clouds, some physical events. We also have different applications in interactive and real-time visualizations. So very different topics, all very interesting. So in these next few slides, we are slowly going to be going over these application domains, and I will demonstrate some of the software we've developed over the last years for these specific research topics. So just to summarize, we are actually specialized in handling different types of data. Mostly we deal with volumes, so 3D images basically, along with other volumetric data sets such as point clouds. We also deal with meshes, segmentations. So for example, if we have images that consist of different objects, we may want to segment those objects a way to handle them differently. We also deal with time varying data, so animations or maybe the same data sets acquired at different times. And we specialize in visualizing this data in a very high performant way. So we try to parallelize our processes, we try to make them concurrent, and mostly also interactive or real time. And for achieving those goals, we often use web technologies. WebGL, WebGPU, and those APIs to access the graphics hardware from the browser. We feel that it's very important to disseminate our research as easily as possible. And if this is achievable just by sharing a quick web link, that's ideal. So, with this in mind, I'd like to start with our efforts to create collaborative visualization applications. So here in these two screenshots, you have two examples of an application which is a collaborative visualization application meant for exploratory tasks, so that medical staff, radiologists in specific, can view images that are acquired through CT scans or maybe MRI scans, and to share those images, share those exploration processes by annotating these images. So here we have quite large 3D data sets. These are quite large volumes. And here the users can annotate these data sets, they can post comments, they can attach questions or maybe some emphasis on different parts inside the actual volume, so inside the actual 3D space. So this is all done as a web-based application. As I said, a significant part of our software is web-based, and we try to make our findings as widely available as possible. So here we are dealing with questions related to content management. So how to allow our users to upload their own data sets, how to make those data sets available for other users as well, and how to attach some additional data to those data sets, which are inherently 3D. So in this case, also the camera views can be aligned. So this is actually a collaborative experience. We've also applied these same techniques to LiDAR data for supporting visualization of point clouds in augmented reality, for example. So my research is mostly oriented towards volume rendering. Also, as you've seen in the previous two screenshots, we have lots of volumetric data, and these volumes are relatively difficult to render, to visualize properly. So we've developed a framework, basically a library for visualizing different volumes. And we have implemented also a large array of several of state-of-the-art methods, ranging from simple methods that have been in common use for the last 20 or 30 years. So if there are some of you in the audience that are dealing with volume rendering software, such as ParaView, for example, which is quite popular, usually those frameworks only use simpler volume rendering techniques, such as the emission absorption model. So no scattering events. Here in our application, we try to implement several of these methods, also taking into account volumetric scattering, different light sources, and also we've encountered different challenges related to the data itself. So some methods are more suitable in a certain setting for certain data types as other methods. So here in this example, in these two screenshots, we have a volume from the medical domain, which is a CT scan of the upper part of a human torso and the head. And the technique to render this volume is actually quite different from the rendering that's been used in the right image, which is a microscopic image of cellular compartments inside uh, a bladder cell. So here we can see that the types of data are quite different. Also, the techniques must be different in these cases. So you can imagine that also if we apply these same techniques to the astronomical domain, obviously it would require tweaking these techniques and methods quite a lot. This last example was an example of crowded volumes, and this has been my main occupation for the last, let's say, 5 years. It's been part of my PhD, and I've been dealing with data which volumes which contain a lot of different structures. So these structures can be different depending on the domain in which they are acquired. So here in these images, I have an example of a CT scan of a specific material. It's a fiber reinforced polymer which is in high demand in automotive and aerospace industries for its low cost, high availability, and it's quite simple to produce actually. And the structure of such materials depends, the strength of such material depends on the structure, on the distribution of the fibers and their length, their orientation inside the volume. And here we have been collaborating with the University of Applied Sciences of Upper Austria and University of Passau, where the researchers have been interested in visualizing such volumes, and they've been unable to clearly see the distributions of these fibers because their images, their volumes were so crowded, so densely populated, so that the classical traditional rendering techniques just failed to work properly. So here in this case, we've developed a rendering system, a visualization system we named the volume conductor, which allows you to group these instances in specific groups based on their attributes. So here, for example, I can take the fibers which are quite short and color them red, for example. And I can also take fibers that are bent or broken, and I can color them blue, for example. Here, I really hope this is seen on the stream. But yeah, you can use colors in different ways to emphasize structures with different properties. And also this can obviously be applied to astronomical data, for example, as well. So for example, you are constantly working with large amounts of astronomical objects, stars, black holes, and so on and so on. And the density, the sheer numbers of these objects can be so overwhelming that just normal existing methods are unable to handle those objects effectively. So here with the volume conductor, for example, you can clearly group together objects with specific properties. So you can, for example, clearly emphasize stars with such and such emissive spectra and so on. And here in the last two images, for example, I've colored the different fibers based on their orientation. So you can clearly see that these fibers, which are in vertical orientation, are actually quite overwhelming here in this volume. And in the last image here on the far right, about 80% of these fibers have been removed, and you can clearly see that the distribution of the orientation of these fibers is now more or less uniform. So also this is a tool that can help you get a fast, a quick idea, a quick overview of the distributions of different objects in your data. So this can be really helpful for the initial exploration of your data sets. So just to get a quick overview and to quickly identify areas of your data which need then further examination. Then this has been proven quite a challenge for human perception. So when you look at those images, if those visualizations contain lots and lots of different structures then on the screen, it can be quite overwhelming for the user. So we quickly identified this as a problem, as a challenge actually, and we've conducted a crowdsourced study of user depth perception in such crowded images. And here we actually came to different conclusions, which actually revealed to us that such volumes, such crowded environments necessitate specific visualization techniques, specific ways of emphasizing different objects, shading them, using colors and color intensity in different creative ways to convey different information about the depth, size, orientation of your objects in the scene. So this has been quite an important achievement, and we would love to apply what we've learned also to the astronomical domain. Here with this volume conductor system, we were quite successful in applying our techniques, in applying this software to different domains. And another domain which we've been actively working on is microbiology. And here we've been collaborating with the Institute for Cell Biology, which is part of the Faculty of Medicine here at the University of Ljubljana. And the researchers there have a focused ion beam scanning electron microscope that is capable of producing quite large microscopic images of cellular organelles, for example. This has been quite a large research on our part, where we had to first segment those instances. We just received raw images, raw data, such as the one on the left, and we've constructed a whole pipeline to get from a raw image through segmentation. And we've also extracted different attributes for each instance. So for example, these attributes in our case were volume, surface area, type of the cellular organelle, orientation, some shape parameters, and so on and so on. And lastly, we've input those data into the volume conductor system and managed to get a rendering such as the one on this in this right image. So this has been quite a leap forward from the visualization software that's typically used in this microbiological domain, and it was instrumental in understanding the cellular processes that are happening inside a living cell. Okay, so this next application was on cryo-ET data. This was a part of the research conducted by Ciril. So Ciril, you can maybe explain some more about this data.
Sure. So welcome everyone also from me. So in this research, what we did is we actually segmented also microbiological data, but with different acquisition method. Precisely, it was cryo-EM, and cryo-EM actually is known to have a very noisy. So it has a really low signal-to-noise ratio. And you can see here in this image that, for instance, there is one slice of volume in the left. Then there is just a pre-filtering, like low-pass filtering and contrast enhancement done for the first part of the volume. And you can see that you cannot see pretty much anything. That's just a block. But then what we did is we actually trained our own deep model for segmentation, and we first did the foreground background segmentation. So in our case, background was noise, foreground were were the structures we were interested in. And then we further improved that by doing 4-class segmentation, which you can see in the final image. And there in the final image, you can actually see individual virions of SARS-CoV. We were actually one of the first one at the time to actually visualize this when the data was available. You can also see here in this visualization that there are specific errors in tomographic reconstruction. You can see that the virions are actually open, and you can see inside. This is not a visualization issue. This is how the data looks like. And data is such because of the acquisition process. So it's not the real thing. There shouldn't be any holes there. But yeah, due to the limited angle of acquisition, the tomography cannot reconstruct all the information in this so-called missing wedge. And here what we did is we did this visualization actually in real time on the web, which were again quite big volumes, volumes of size of more than 1K cube. And yeah, they run on commodity hardware, not really an average integrated GPU. It needs to be dedicated gaming GPU at least to be able to render this in real time. What we did further is that we also implemented the model, the deep inference, in the browser, which is additional benefit for users because they don't have to share data with anyone. They can do it on their own hardware without utilizing any servers. So this means that the data doesn't leave your computer, and this is really good for when the institutions or groups have privacy issues. Yeah, but yeah, we are further developing this. Maybe we can discuss this at some later point during the question session. Next slide, please. So what we also did, like I shown that there are some errors in the tomographic reconstruction. What we did is we actually implemented our own tomographic reconstruction method, which minimizes the noise in the reconstructed result, so in the reconstructed volume. And here you can see basically on the left, the turquoise, the first turquoise row, you can see, yes, the left part is actually the traditional approach that is used in most microbiological labs at the time. And you can see that this is really noisy. Then you can see the state of the art before our approach in the middle, which is some deep approach. But in our case, we didn't even deep approach. We actually did a local optimization method with non-local mean, and this proved to actually eliminate a lot of noise in our case. Now, more on this is at some point we also tried to make the whole cryo-ET microscope differentiable. Differentiable meaning that you actually create a simulator, a forward simulator, where you can simulate what is happening in electron microscope, and you try to do this as precisely as possible. And you can get really close to the real thing by simulating the physics up to the highest degree. But then the thing is that once you get the images, you cannot really do any assumptions on what they were made from. And this means that you can at some point think about reversing the process, so to actually go from the image to the specimen. And in our case, we actually inverted, which means we made several steps of microscope differentiable, and this was used for denoising, and it proved to work very nice as well. It was actually pretty much similar results in matter of numbers to the one that I mentioned beforehand. And such differentiable approaches are actually nowadays becoming very popular, especially in physics, where you can use that for different tasks. Probably some of you heard about physics-informed neural networks, and that's pretty much it. This is actually the approach for physics, where you can actually train the neural network by simulating the forward simulation. But on the other hand, you can implement your code in a differentiable way, which means that you can do optimization using gradient descent, which is probably some of you know actually the approach of deep learning, but deep learning is only one of the subfields of differentiable programming, which has a much broader scope than just developing deep models. And this is where we are actually trying to go now for certain things, especially related to graphics. And this proves to be very popular field at the moment, which means it's very competitive as well. Next slide, please. So what we also tackled in our laboratory is that at some point we were contacted. Actually, I reached out to some contacts at CERN, and they got back to us, and we identified that for certain specific challenge they had in mind for some use case, they needed visualization of particle collision events in CMS collider in CERN, and they asked if we can help them with that. And at the time, we were actually developing our own web-based visualization framework for visualization of 3D graphics, mostly mesh geometry, but also point clouds. And this actually helped us out a lot by with development of this approach. And this is actually still online. So that challenge, that Kaggle challenge, was very successful. The Kaggle challenge was originally there for using deep learning for reconstructing the trajectories of individual particles in these collisions from these different points of hits in the collider. No, sorry, not in the collider, in detector. And we actually visualized those. And this was, our tool was actually quite popular during that Kaggle challenge, and it's still in use in some specific use cases. We are further developing our web-based visualization system, which is now partially specifically tailored for some extreme data processing pipelines that they have at pipeline at CERN. And what we're helping them with is actually they're using our library in a new version of their internal software, which is called Root, and some of you might know about it because it was used also in some other domains. And this is actually they are actually rebuilding Root as a web accessible system, and our library will be there to support visualization, which I believe is quite a nice achievement. So here, what we tackle is we tackle a very highly customizable rendering pipeline, where you can actually define the stages in your visualization pipeline completely on your own, and then execute the whole visualization pipeline in a seamless way, which then runs in a browser. We originally developed this in WebGL, which was a bit older technology for web, the first native, so to say, native GPU accelerated visualization framework for browsers. But now we actually migrated to WebGPU, which is the newest standard now. And yeah, we are pushing this forward. Next slide, please. So the next domain that we tackled is point cloud rendering, augmentation, reconstruction, and this was mostly done on LiDAR data acquired from the airplanes, especially for Slovenian terrain, which we had access to. And in reconstruction, what we did is we reconstructed surfaces which were not acquired during the acquisition, which is water surfaces, as you can see in the first example. So the whole lakes were missing their surfaces. and we actually reconstructed those from that missing geometry from the neighboring data. And similarly, you can imagine that when you're acquiring data from airplanes, you do it from bird perspective. So when you're shooting with laser down to Earth, there are obstructions, and you cannot really acquire information in the portions of the terrain that you cannot see, or in portions of buildings that you cannot see. And what we did there is we actually used data fusion approach, where we took the data that the geodetic researchers already have available, like cadastre, like terrain data, and like building data, and so on. And we use that data to reconstruct the missing data in the point clouds, which means we added missing walls to the building. We reconstructed bridges, because we have information in geodetic databases on how bridges look like, how wide they are, how thick they are, and so on. And we were actually able to reconstruct those bridges, which can be seen in the bottom left image in the presentation. And of course, you don't have the water surface under the bridge, so we reconstructed that as well. Then another tricky part was reconstructing the overhangs in the mountains, because overhangs, of course, cannot be easily acquired from the airplane with lidar. So what we did there is we did polynomial interpolation of the missing data from the neighboring regions. So we filled up those holes, and for visualization purposes, this is actually very good. Of course, this is not the real data because you just don't have it, but it fills in the holes for purposes of visualization, which is very nice. And currently, what we are tackling is point cloud visualization on city level, where you actually acquire data using different acquisition techniques, either from airplane or from drones or from cars or from terrestrial sensors. You fuse that data, you link it with the color, of course. These sensors, they do that. I mean, today's equipment does that during the acquisition process. Previously, we had to do that manually, but yeah, now you have that, and we are actually tackling the problem of visualizing really large point clouds in real time on the web, and that is our ongoing research in this domain. But we also want to segment it, so segment individual objects from point clouds. And yeah, this would be what we are currently doing in this domain. Can we go to the next slide?
Maybe just one thing to add
Sure.
here. It's quite a large use case for the municipality of Ljubljana. They want to do urban planning with this, so
Yes.
they want a tool that could be that could easily allow them to edit those point clouds, to add objects to them, and see how potential scenarios for urban planning would turn out.
And also to remove specific things. For instance, or if you demolish certain building, what you can build there. And their idea is to actually put all this in VR, which is a bit go a bit further along the timeline. But yeah, maybe at some point we will also achieve that. So, and yeah, this is our last slide for the things we're doing. So we do quite a lot of VR related research in the laboratory, which is mostly related nowadays to perception and to learning, which we don't have here. But what we do have here is the examples for outreach. For instance, what we developed is a system for automatic generation of documentaries, interactive documentaries in VR from mesoscale molecular models. So if you can imagine having like whole cell or part of cell reconstructed down to or built up from individual atoms, which then they group into molecules, which group into different shapes like proteins and other things, and they build up everything in the scene. So for such scenes, we actually developed automated documentary generation tool, which takes you through these scenes based on structures which are there. So it analyzes the scene hierarchy, it identifies objects which are there, and then it actually generates the narrative and does the path planning and takes you through the scene, which this path, this traversal can be different for every execution, and you can pause it at any point, and this system is actually also explaining you what is happening along the way. So it explains which structures you're looking at the moment. It makes pauses and shows you individual structure that is being explained. It can do cut planes. It can sparsify. Of course, it needs to sparsify the scene because otherwise you would only see black plasma and nothing else in this environment. And this was actually quite nicely received at the best visualization conference. And this is actually a really nice tool. Then what we did technical research wise is we were improving the performance of rendering such really big scenes. Such scenes can be composed up to 100 millions of atoms, and it all runs in real time in VR glasses. So this means stereoscopic rendering. It's not deployed on the headset. It still needs a full computer to run on, but still this is quite impressive. And yeah, there was some follow-up work where I was not involved, where they actually reached the level of visualizing 1 billion atoms from procedurally generated scene on the fly. So another thing that we tackled here, so this what you see on top right, what we did is long time ago, that this was probably almost 15 years ago. So when first Street View came out, what we did is we actually scraped Street View for specific path from point A to point B, and rendered it in stereoscopic visualization on the headset, and then we played it along. So you could actually be on the virtual trip from point A to point B, tilting your head, looking around yourself, and there was some interpolation between the frames so that it wasn't just sequential jumping from frame to frame, and this proved at that time quite nice. But a little bit later, what we also investigated was the collaborative visualization environment in VR on the web. At that time, web VR was very popular, and what we did is we actually linked it to the system that Žiga presented in the first slide, and had VR on the web with collaborative functionality. So you could also use pointers. You could have the same functionality as there, which was very nice. And this, I believe, would be it, and I would give the word back to you, Žiga.
Okay, so I'm gonna wrap this up with some thoughts about how our potential future work would look like. And yes, right now we are planning to expand our research into the domain of astronomy, astrophysics. So we are looking for use cases in these domains. We are trying to find some novel use cases to apply our techniques in. So specifically, for example, my work with grouping, with interactive visualization, with sparsification and so on, how this could be applied to large data sets that you are dealing with. So we already have some collaboration going on with ESA. We are trying to visualize some of them, some of their data gathered with Gaia, and they have it's quite a large data set, and visualizing it in an intuitive way, trying to emphasize things, objects, events that we are actually interested in proves to be quite a challenge. Also, we have a potential collaboration with a researcher working on tidal disruption events. So they are exploring what happens to planets and stars around massive black holes. And this it's quite interesting to see just simulation-wise what happens. But to visualize these things, these events in detail, trying to emphasize different objects there in those simulations is quite a challenge. Obviously, there's quite a wide range of different visualization systems already available, but in my experience, they are using just older, proven to be useful techniques. But I think it's quite a nice use case for more modern techniques to be experimented with. Also, in these cases, when you are working with quite heavy objects, black holes and whatnot, I've begun to actively explore the area of relativistic ray tracing. So you may have heard that ray tracing, especially in the graphics community, is beginning to become more and more popular as a feasible method for displaying 3D scenes, 3D environments, because the graphics hardware, graphics cards have become quite strong, quite powerful and fast. And it's possible nowadays to use ray tracing to get real-time computer-generated imagery on your screen. And it's become a new challenge to incorporate some relativistic effects here. So you can simulate lensing events, for example, and uh, event horizons and whatnot. So such effects can be quite a challenge to visual. Anything else, it's a technique that can be useful for creating really nice images for the popularization of these scientific areas. So these are some of the ideas we have. These are some of the research directions that we are pushing towards in these last months, let's say. And we are quite excited to present this to you today. So maybe you can find some new use cases that we could work on, we could collaborate on. And yeah, we'll see where this takes us. I think we have a lot of potential here, especially because you are dealing with large amounts of data with a ton of different attributes. You are dealing with volumes, with images, with point clouds, basically with everything that we are quite familiar with in our laboratories. So with this in mind, I really hope we are going to start a fruitful collaboration with you guys, and yeah, we'll see where this takes us. So thanks for the invitation. I would like to invite you to contact us with any further questions you have, with if you have any further inquiries about specifics of our work. And here is some contact information on how to reach us. And yes, thank you for listening to us ramble on for 45 minutes. So Priscilla, take it away from here.
Thank you so much. I'm sorry, Cyril, I didn't introduce you. I didn't realize it was a joint presentation, but it was a great presentation. Yeah, it's a very interesting work that you're doing at the University of Ljubljana, and I'm sure it will have plenty of applications in the future for us. Gaia was like the first revolution in volumes of data, and especially for our TVS collaboration, LSST will be the next revolution in data volumes. So, yeah, I'm sure there is room for plenty of collaboration. Thank you so much to both of you.
Thank you.